This story started years ago. I was reading an article in some technology magazine about Playboy millionaire who apparently wanted to put laptop batteries in a sports car. I thought, what a silly idea. First of all, laptop batteries never last. And second, who would want to drive a sports car without sound of a great V8 engine? Well, I guess you know the rest of that story. And now, a few years later, I'm obsessed with the idea of making an electric car. I needed to start somewhere, so I decided, of course, to look on what's available on the internet. This is where I stumbled upon an open inverter forum. On this forum, many enthusiasts convert their cars to electric using various OEM components from crashed or decommissioned cars. I thought that it might be a good idea to get the electric drivetrain working first, and after that sort out the battery. My attention was attracted to the Toyota Prius inverter, an electric motor used in the Prius gearbox. Toyota was very successful with the Prius, and as a result, this car is ubiquitous in many cities and towns, and this means some of the parts could be had very cheaply. I found that 𝗧𝗶𝗺𝗀𝗀𝗀 designed a PCB that can replace the processor board inside the Prius inverter, so it can be controlled using open inverter software. I decided to go a slightly more complicated and cheaper route, so I used 𝗧𝗶𝗺𝗀's designs and I ordered the board from 𝗧𝗶𝗺𝗀𝗀. A few weeks later, boards have arrived from China, and I engaged myself in another fun task of trimming the board because it was not fitting into the inverter model that I had. So I had to cut some of the corners and I had to trim side of the PCB so it can fit into the inverter. Also, some of the connectors were not soldered in, and I had to solder the connectors to start testing the board. Okay, so now we connected the 12 volts and we have indication that power is working. We need to check the main supply voltages. So we have all our power in place. Now we need to program the STM32 module. STM32 was programmed flawlessly, which cannot be said about ESP8266 Wi-Fi board, which I had a few troubles programming due to the fault in the serial cable that I had to use. Having endured some minor hair loss and consumed few cups of coffee, I finally managed to resolve this, and this had led me to exciting times of actually testing the inverter. To start the inverter, as well as 12 volt supply, I will need to connect MG forward in pin to the 12 volts as well, and I will start the inverter in the manual mode. Here I am connecting pin 3, which is MG forward in signal. I am using the test link wires just to connect pin 1 and pin 3 together and to connect them to 12 volts. Now I'm connecting DC to DC converter connections as well as the 50-pin JST connector. First I tested the power with the current limited to 200 milliamps to ensure that nothing is short-circuited in the board and not drawing too much current. Now I can connect both pins together and actually enable the power from the power supply to be delivered to the PCB. And we can see now that LED is on and flashing. And now I want to test the firmware update through the Wi-Fi. So once we connect it and console is up and running, we can choose the update option to update firmware. And I want to start the experiment from just using a simple assigned firmware in this case. So I've selected a bin file and chose to upload. And now we can see the progress of upload. And you can see that green LED is flashing on the Wi-Fi module, which means that the data has been transferred. And once the red LED on the board is flashing, then it means the firmware is ready. Whenever electric motor is driven, the IGBT transistors switch electric current through various coils of the electric motor. So for the open inverter board to control those IGBT transistors, it has to provide PWM signal. PWM stands for pulse width modulated signal, and this signal is controlling the IGBT transistors in the inverter. So first, to test the inverter, I need to run it in the manual mode and measure PWM signal produced by the processor. Okay, just pick up the ground from here. Excellent. And now we started the inverter So this is channel 1. That is quite strange. I'm not getting PWM signals. Crikey. Right, I'm getting some strange interference. Let's just check the power line. Ooh, same thing on the 3 volts. What the hell is going on? Well, I'm not sure. I think I may have to try another board. Right, I'm back again. I could not believe it. I've just spent half an hour just trying to troubleshoot this issue. And actually it's turned out to be the damn probe again. I thought it was a problem with the power supply. Maybe it was just going into some sort of oscillation mode. Turned out to be I've just replaced the cable. And here we go. I'm just measuring. This is our PWM signal. I just need to synchronize it. Here we go. Beautiful. Right, let me see if I can stop the inverter. Yep, I stopped the inverter and you can see that PWM signal is gone now. Again, start the inverter in manual mode and we have our signal back. Now PWM signal is working, so the next step would be to connect the inverter to my motor, aka gearbox, and actually run it in so-called open loop mode. This is the gearbox and we have a cable for MG1 and we have cable for MG2. I think unfortunately they've been cut off and I will be using MG2 cable only. Also, I purchased an seal connector and soldered a little interface board. So this cable, ribbon cable, will be plugged in into the inverter board here. I'm fitting the inverter cover and inserting the ribbon cable in the side cutout of the inverter. The seal connector will be installed using existing plastic fitting, but I'll have to slightly modify it. For now, I will be just using it as it is. To get the whole thing tested, I needed to sort out the high voltage cable first. Unfortunately, whoever dismantled this inverter just brutally cut the cable off rather than removing it. So I spliced the cable together and now it's ready to connect to the inverter. Once the cable is there, we can actually start the test. At first, I've just connected the bulb as my pre-charge resistor. I've had a fuse and a switch. The switch will allow me to go from the pre-charge mode to the normal operation mode. Once I turn the supply on, the bulb should light up. The current should be passing through the bulb and supplying the high voltage to the inverter. Okay, I powered on both power supplies, but for whatever strange reason the lamp is not lighting up. Right, I want to try again. This time I want to use the current clamp meter to see whether actually any current is passing to my inverter. That's like 0.4 amps, so it's really doesn't make any difference. I decided to analyze the problem properly and start from the place where I was last time, but first I started to removing the inverter cover, and I found that when I was first mounting the board and testing PWM signals, I forgot to attach the bolts that actually connect IGBTs to the output that goes to the motor. So after that I carefully assembled everything again and found that it's all started to work. So now I'll show you what actually went wrong and what did I forget to fit in the connection side of things. And now I can remove the cable itself. And now I can remove the cover. Yeah, basically when I assembled the inverter first time, I put this frame in. So I put all these screws in place and all of these, but I forgot to put these screws. So basically all of the row of those 3 screws and those 3 screws were missing. It was a bit ironic, but effectively that's where IGBTs are, down there on that bottom board here, and that's how they transfer the signal to these connections. Our motor, of course, is connected to these 3 connections here. First, I'm switching a low voltage power supply, which is powering the open inverter board, and now I'm switching the two power supplies that provide so-called high voltage, and with a bit of a delay I'm now doing effectively pre-charge, so the current is flowing through the bulb. By switching the switch I will bypass the bulb and then current will flow directly. Now I'm starting open inverter console and selecting AB, which is basically means no encoder, and going to the testing section, which basically I will set up norm to 100 and F slips to 10. And we are spinning. We can rotate the motor in a sine mode. So the next step would be to actually work with the FOC firmware. So it's a field-oriented control firmware. And to do this, I will need to wire up the resolver and wire up a pedal. And next step would be to start tuning the motor using FOC firmware. Well, I suspect that's where the resolver is connected. As I don't have an original Toyota connector, I'm planning just put wires like this. Right, so I have these two strands of wires, but one of the dilemmas that I'm facing is actually a resolver supposed to have 6 wires, and this one has 2 extra wires, and I'm not really sure what they are for. So I've decided to try testing resistance of these wires. So I'm checking my DVM, well, it's working well, and let's start from those two. Right, that's 13 ohms. It's brilliant. If I think this is what it is, 13 ohms might be an exciter for the resolver, and that's 21.6 ohm. It's even better news. So if this one is similar, then it's definitely a resolver. Bingo. So that's also 20.2, and this one is 21.7. I think they're almost the same, where the first pair is clearly less. It's 13 ohms, so that's clearly an exciter. And these two other pairs, and that would be part of the resolver, sine and cosine. We'll still need to determine which one is which. But what's about the last two? Well, last two clearly have much higher resistance. It's 56 kilo ohms. So that could be something completely different. So I wonder whether this could be a temperature sensor.
So here's the junction block. We've got a pass-through connector for the MG1 resolver and the MG1 temperature sensor.
Let's keep those two apart, but all those 3 on one side and those 3 on the other side are actually resolver wires. To finish off my preparation for the field-oriented control tuning, I needed to wire up a pedal and the resolver, of course. So I had to wire up and make up the cable that connected to the amp seal connector. At the same time, the pedal had number of connections to provide a feedback signal from wiper 1 and wiper 2. So those are connected to appropriate acceleration and regen connections on the open inverter board. First, I need to start connecting resolver wires. So I split them in 3 pairs. So effectively this our exciter, and those two would be our sine and cosine, which of course we don't know which one is which. But you know, let's give it a try. Okay, I connected the resolver. So I tried to use a method recommended by Damien in this FOC tuning video, although I wasn't sure I was getting the right connection there. And I went on the internet and I found the drawing of the connector for the resolver for MG1. So yeah, basically according to this diagram, the connection, obviously those two black and yellow are the temperature sensor, and then the white wire on this side closest to me would be the cosine, and the gray wire, which looks pretty much like white, it's a sine, and then the purple wire it's exciter, and the opposite side, the brown one, is the exciter, and the red is cosine return, and orange is a sine. I was a bit apprehensive before starting FOC tuning, as it proved to be tricky for many. However, it was absolutely necessary for me to try it. Right, so now I'm going to rotate the motor, and we're going to see what's happening with the signal. Okay, so we are getting good reading now, and you can see that the encoder is reading from 0 to 360 degrees. To start testing current sensors, I will need to program some initial parameters into the inverter. I will start from pole pairs and resolver pole pairs. So we use 4 and 2 for these parameters, Then I will select resolver mode and followed by frequency 4.4 kHz and enter EL1 gain and EL2 gain as 3.09 degrees per ampere. Next important parameter is pin swap. I need to set pin swap to PWM output to 3. Let me explain what pin swap means and why do I need to set this value. Basically what it is, most of the inverter manufacturers, they sense PWM1 and PWM2 with the current sensor, so PWM3 is not sensed at all. However, Toyota, they do something different. So Toyota sends PWM2 and PWM3, and PWM1 is not sensed at all. So what pin swap does is actually swaps the current sensors, so they will monitor PWM signals in a Toyota way. To finish off, I need to set UDC minimum to 0, as my voltage is only 60, and change the temperature maximum to 150. Last thing I need to do is just to save the parameters to flash. I removed my pliers so that this one will not sort of jam into anything, and just entered manual ID 1 amp. So I can hear a bit of a whine, but that's about it. Now I entered manual ID 3 amps and I can see that my bulb is now illuminating. So now I'm setting current to 3 amps, nothing, 4 amps, and we have rotation, 5 amps. Let's try a bit more, 6 amps. It's rotating nicely. And now I've got back to 0 amps and it's stopped. The power supply on, so that's powering an inverter. And now the high voltage supply going through the bulb just to pre-charge. This one is on, and now I'm just gonna press the start button. You can hear a bit of a whine. That means that inverter has started. And now we have a throttle control. But anyway, yay! We actually succeeded. So the sync-offs value that I found seems to be working well. Let's have a look at the graph. I plot the graph of the resolver. So we are getting variable speed. Yeah, it seems to be working. I'm not really sure why. It seems to be accelerated more at the beginning and then less. So now you can see this, my pedal control. Another little success. And lastly, I did a little experiment where I enable current sensors IL1 and IL2 and plotted the graph of resolver angle and current sensors. On this graph we could see how current changes with the application of the throttle and angle change relatively to the current. With MG1 job out of the way, I swiftly reconnected the cable over to MG2. It was actually much easier because the cable itself was made for MG2 in the first place, and I've just used it for MG1 while I was doing the testing. I performed tuning pretty much in the same order as I did with MG1, only I found the sync-offs value was much higher for MG2 in comparison to MG1. The final sync-off value was found at 20,200. Now I'm gonna try and verify, see if it works with the throttle control. It's working with the pedal, baby. Look at that beauty. It's going. MG1 and the wheels. That's well done. Let me show you the pedal and me controlling it by hand. Thank you very much for watching. It was a bit of a long video this time, but I hope you enjoyed it. If you do have any questions, please ask in the comments down below. If you did like the video, you may want to watch this playlist over here where I put more detailed videos about the conversion. And please give us a like, and I will see you in the next video.